Welcome everyone for today's class. In this class, we are going to discuss about thermal analysis. What is thermal analysis? Thermal analysis is a branch of materials science where the properties of materials are studied as the change with the temperature. That is, the change of the properties of the materials are studied with respect to temperature. When matter is heated, it undergoes certain physical and chemical changes. For example, if it is the physical changes, it includes phase changes such as melting, vaporization, crystallization, transition between crystal structures, changes in microstructure in metal alloys and polymers. Volume changes if the volume changes means the expansion of the volume or the contraction of the volume, and changes in mechanical behavior. Chemical changes and the chemical changes include reactions to form new products, oxidation, corrosion, decomposition, dehydration, chemisorption, and so on. These physical and chemical changes take place over a wide temperature range. So now we know what is thermal analysis. Thermal analysis is a branch of material science where the properties of materials are studied as they change with the temperature. Then here the change of the properties with respect to the temperature we are going to study in thermal analysis. Materials are used over a wide range of temperatures from Arctic cold to tropical heat in corrosive environments, variable humidity, and under load, that is stress. It is necessary to characterize the materials and their behavior over a range of temperatures to determine what materials are suitable for specific uses and to determine what temperature range materials or chemicals can withstand without changing. This sort of information is used to predict safe operating conditions for products, such as which type of tire materials is best for vehicles in extremely cold or extremely hot climates, the average expected lifetime of the material, such as paints, polymers exposed to temperature changes. Therefore, so here the thermal analysis, the mainly major advantages of this is it is predict the safe operating conditions for the products like the paints, polymers, and etc. Then we shall discuss about the types of thermal analysis. There are several types of thermal analysis. They are thermogravimetric analysis TGA, differential thermal analysis DTA, and differential scanning calorimetry DSC, and TT thermometric titration DMA dynamic mechanical analysis, and TMA thermomechanical analysis. So these are all the some of the thermal analysis. So in this class we are going to discuss only about thermogravimetric analysis. This is, so in the next class we'll discuss about differential thermal analysis. And so what is thermogravimetric analysis? In thermogravimetric analysis, the sample is heated in a given environment at controlled rate. The environment may be air, that is in the oxygen, or in the nitrogen, carbon dioxide, helium, or argon, so etc. The principle of thermogravimetric or the TGA analysis is the sample is heated in a given environment at controlled rate, then the change in the weight of the substance is recorded as a function of temperature or time. So the temperature is increased at a constant rate for a known initial weight of the substance, and the change in weights are recorded as a function of temperature at different time interval. So this plot of weight change against temperature is called thermogravimetric curve or thermogram. Now we know what is the principle of thermogravimetric analysis. In thermogravimetric analysis, the sample is heated in a given environment at controlled rate. So when we are heating in the given environment at controlled rate, the change of the weight of the substance is recorded as the function of temperature or time. From this only we are going to analyze the substance. The graph drawn between the change of the temperature or time, change of weight change with respect to temperature is plotted. That plot is called as thermogram or thermogravimetric curve. For example, we can take this is the thermogravimetric curve for silver nitrate. So here the horizontal portion of the curve indicates that there is no change in weights, that is AB and CD. If you see in this, so AB, this curve, and CD curve is here, and the portion BC indicates that there is weight changes. Here the weight changes happening. So the curve AB and CD or shows that there is no weight change, and the curve between B and C shows that the change in weight of the substance with respect to temperature. Here in the silver nitrate, the weight of the substance, that is silver nitrate, remains constant up to that is up to temperature 473 degrees Celsius, indicating that that is the silver nitrate is not thermally stable up to temperature of 473 degrees Celsius. So at this temperature starts losing its weight, and this at this temperature means from the 473 degrees Celsius onwards it starts to lose its weight, and this indicates that the decomposition starts at this temperature, and then it decomposes to the silver nitrate is decomposed into the silver and NO2 and into the oxygen. So the loss in weights continues up to 680 degrees Celsius, leaving metallic silver as the stable residue. Beyond this temperature, the weight of the sample remains constant. So beyond this temperature means this is after this temperature, the weight of the substance becomes the constant, that is C and D. The curve shows that the C and D. So here we could understood that here this curve shows that there is no weight change in the silver nitrate, and this curve also shows that there is no weight change. There is only weight changes happening in between this 2 points. So which shows that here when we are increasing the temperature, so there is change in the weight, that is especially the loss of weight is happening in this. So by using this we can find that the characteristics of the substance we are going to analyze here. Then the instrumentation. Here we have the in this we shall see the modern instrumentation of thermogravimetric analysis. That is, the modern TGA equipment has a sensitive balance, usually a micro balance for continuously measuring a sample weight, a furnace surrounding a sample holder, and a purge gas system for providing inert or reactive atmosphere. A computer generally controls the furnace and the data that measures, that is weight versus the sample temperature, is collected and processed by computer. Several modern analytical microbalances are commercially available. Torsion balances, for example, torsion balances, spring balances, and electro balances. In general, the balances is designed so that a change in sample weight generates an electrical signal proportional to the weight change. So the balance is designed like this only. The electrical signal should be proportional to the weight change. The electrical signal is transformed into weight or weight loss by the data processing system and plotted on the y-axis of the thermal curve. So weight changes plotted in the y-axis and the temperature changes taken in the x-axis. Here we have the black diagram of thermogravimetric analysis. So in this black diagram, I have given some of the important instruments we are using in this instrumentation of thermogravimetric analysis. Here they are atmosphere control, furnace, sample holder, temperature sensor, balance control, and recorder. So in this, this is called the sample. Here we are keeping the sample, and the sample is used to heat by using the furnace temperature. This is the furnace temperature. By using this, we are increasing the temperature. Here temperature is censored by using this temperature sensor. The change of the temperature is recorded by this balance, the recording balance, and this temperature change also recorded by the recorder. This here we kept the balance control, and here change of the weight and change of the according to change of the temperature is recorded by the recorded. So by recording we can get the change of weight of the substance we have taken with respect to the temperature. So if you plotting the thermogravimetric curve, that is with respect to the change in the temperature, the graph is plotted between the change in weight with respect to change in the temperature. The thermogravimetric in this TG balances are available for sample masses from 1 to 1000 milligram, with the usual sample weighing between 5 to 20 milligram. So it is measured 1 to 1000 milligram, but usually sample weighing between this amount 5 and 20 milligram. There are specialized high capacity thermogravimetric analysis systems available that can accommodate samples of up to 100 milligram too. So we can measure up to 100 milligram. The balance itself must be thermally isolated from the furnace, although the sample holder and the sample must be in the furnace. Here the balance itself must be thermally isolated from the furnace. So although the samples holder and the sample must be in the furnace, we should even though we have the sample holder and also the sample is in the furnace, we should isolate the balance thermally. There are two possible configurations of the balance and furnace. They are horizontal furnace or a vertical furnace. Both types of the configuration suffer from drift as the temperature increases. When increases sometimes there is fall in the temperature, the fall in this measurements, and the vertical configuration suffer from buoyancy effects due to the change in gas density with temperature. The horizontal configurations was designed to minimize buoyancy effects, but horizontal configurations experience changes in the length of quartz rod connecting the sample to the balance as the temperature changes. So this is the black diagram of thermo. The first one we have given, this is the black diagram of a TGA system. So here the S represents the sample pan hanging from the balance arm in position in the furnace, that is represented by the solid bars on each side. And then we have the second schematic diagram, which shows that a commercial thermogravimetric analysis showing the purge gas inlet and outlet and the thermocouple position behind the sample pan. If you see in the first diagram, this is, in this we have the here we are keeping the sample is kept in between this furnace, and we are increasing the temperature. When you are increasing the temperature is changes, and the temperature, when the temperature changes, the change of the weight also changed, so that the change of the temperature changes is recorded through this way, and the change of the weight of the substance is recorded by the balance, and mass changes recorded by this data acquisitions. So that here to heat this furnace, to increase the temperature of the furnace, we are connected the furnace, this is, with the sample. So by this way we can find the change of the weight according to the change of the temperature. It is recorded and measured, and we are, by the plot between the change in weight with respect to the change in temperature, we can get the graph. From that graph we can analyze the substance, and this is the electrobalance for a TGA. So as the sample weight changes, the balance arm tips, resulting in a change in the amount of light reaching the photocell. This generates a current to restore the arm position. The current is proportional to the change in weight of the sample we have taken in the sample holder. Here in this, it is the control and balance arms are given, and by using this balance control, we are measuring the change in weight of the sample. And then buoyancy effects and changes in the quartz rod results in error in determining the mass of the sample. The buoyancy effect is an upward force exerted by a fluid that opposes the weight of an immersed object. So the buoyancy effect means, so it is an upward force exerted by a fluid that opposes the weight of an immersed object. And then we saw the balance control, and we have the furnace surrounds the sample and sample holder. It must be capable of being programmed for a linear heating rate. In modern instruments can be heated and cooled rapidly. These instruments that heat at rates of up to 1000 degrees Celsius per minute are available. In the commercial instruments can heat at rates up to 200 degrees Celsius per minute from room temperature to about 1000 degrees Celsius. Cooling by forced air can be done at 50 degrees Celsius per minute. There are furnaces available with upper temperatures of 1500 degrees Celsius, 1700 degrees Celsius, and also available in 2400 degrees Celsius. These higher temperatures instruments are useful for studying refractory materials and engineering materials. The furnace must be able to be purged with a desired gas to provide the correct atmosphere for the experiment, and to remove gaseous products from the sample component. Here we are taking in the furnace, the argon or nitrogen is used when an inert atmosphere is desired. Air is often used for oxidation and combustion studies. Hydrogen may be also used in the furnace to provide a reducing atmosphere with appropriate precautions to prevent explosions. In modern instruments, the modern instrument permit the purge gas to be switched automatically so that the sample can start heating in an inert atmosphere and be switched to air or other reactive gas at high temperatures. For example, the sample holder and any instrument parts inside the furnace, such as the thermocouple for measuring the temperature, must be able to withstand high temperature and be heated at these high temperatures. And also the quartz, platinum and various ceramics are used for the sample holder and other parts. Here till we saw that about the furnace. Now the sample holder. The sample is placed in a sample pan or a crucible made of platinum quartz or ceramic. So ideally the temperature recorded is the exact temperature of the sample. This entails measuring the temperature of the sample while the analysis is carried out. It is particularly important to measure the temperature of the sample rather than that of the furnace. This is difficult because the temperature is measured with a thermocouple that is near but not in the sample. The thermocouple is never inserted directly into the sample because of possible sample contamination. That is contamination of the thermocouple resulting in errors in temperature, so that the thermocouple is never increased directly into the sample. Therefore, the temperature actually recorded may be slightly different from the sample temperature. The sample temperature generally is lower than the temperature recorded by the thermocouple. This is due to the factors such as rate of heating, gas flow, thermal conductivity of the sample and the sample holder. And here so we saw that the temperature actually recorded may be slightly different from the sample temperature. So that is due to the rate of heating, gas flow or thermal conductivity of the sample or sample holder. And then this problem is compounded by the fact that at temperatures below 500 degrees Celsius, most of the heat transferred from the furnace to the sample takes place by convection and conduction. But at temperatures above 500 degrees Celsius, where the furnace is red hot, most of the energy is transferred by radiation. The switch from conduction and convection to radiation energy transfer makes choosing the position of the thermocouple to obtain accurate temperature measurements of the sample a quite complicated problem. So by using this, the switch from the conduction and convection to radiation energy transfer, it reduces this problem. And then the sample preparation has a significant effect in obtaining good data. It is suggested that the maximum the surface area of the sample in TGA can improves the resolution and reproducibility of weight loss by the temperatures. The sample weight affects the accuracy of weight loss measurements. Therefore, the 10 to 20 milligram of sample is prepared in most applications. So if you use the less amount of the sample, it increases the accuracy and reproducibility. So whereas if the sample has volatiles, then for that, if the sample is volatile in nature, we should use 50 to 100 milligram of the sample is considered it is adequate to use if the sample is volatile. And it is to be noted that most thermogravimetric analysis instruments have baseline drift of plus or minus 0.025 milligram, which is plus or minus 0.25% of 10 milligram sample. This is an example for TGA of calcium oxalate monohydrate. We shall discuss about this in later, that is in the next classes. And some of the factors affecting the TGA curve. The major factors affecting the TGA curves are instrumental factors and sample characteristics. So instrumental factors may be the furnace heating rate and the furnace atmosphere, and the sample characteristics include weight of the sample and sample particle size. So instrumental factors are the furnace heating rate and furnace atmosphere. Here the furnace heating rate, how it affects is the temperature at which the compound or a sample decompose depends upon the heating rate. When the heating rate is high, the decomposition temperature is also high. A heating rate of 3.5 degrees Celsius per minute is usually recommended for reliable and reproducible TGA in this. And the furnace atmosphere, inside the furnace surrounding the sample has a profound effect on the decomposition temperature of the sample. A pure nitrogen gas from a cylinder passed through the furnace, which provides an inert atmosphere. And then sample characteristics. So weight of the sample, small weight of the sample is recommended. So if you use the small amount, it could give the exact measurements. So small weight of the sample is recommended using us. When we are using the small weight, that eliminates the existence of temperature gradient, that is the temperature variations through the sample. And particle size of the sample, the particle size should be the smaller and it should be uniform. So if the particle size of the sample is small and uniform, so when we use the small and uniform particle size, so it uses to record, and also it increases the accuracy of the measurements. And if you use the large particle or crystal, may result in apparent very rapid weight loss during heating. So we can avoid if you use the small and uniform sizes of the particle. So in this class we have discussed about the principle of thermogravimetric analysis, and then we have discussed about what are the things or the materials we are using in the instrumentation in thermogravimetric analysis. So we know what is the principle of thermogravimetric analysis. That is, here we are measuring the weight loss of the sample with respect to the change in the temperature. This weight loss and the change in temperature is plotted in a graph and x and y axis. Then we are from that plot we are measuring the properties of the substance. So now we know what is thermogravimetric analysis and what is instrumentation using in the thermogravimetric analysis.